And this is again a video on checksum hashing. I have written down some notes here of my thoughts as well as the methods that I come up with and try to read from them. Now, the coding activities of lossless data compression and data error detection and correction are ironically somewhat identical, yet also the exact opposite of each other at the same time. Trying to define excellent data error detection and correction functions can lead to the discovery of excellent lossless data compression functions, and conversely, defining excellent lossless data compression functions can enormously assist in the definition of excellent error detection and correction functions. For instance, if we can losslessly compress a file enormously by elimination of large amount of redundant information which is always contained in the original information, we can always introduce a bit of small amount of redundancy and replicate that information so as to check against multiple copies of the same information to correct it. Thus, if we have a reasonably small length, we can say take a larger length which is multiple of this and replicate this in different places. So the chances of say 3 of those are there, 2 of them agree, then it must be that value. So divide it into parts here, and these are divided into multiples of so many parts, and they are replicated a small amount. So this is the simplest error detection correction method which can be performed. To that end, the activity of error detection and correction can be conducted and can be performed at 2 levels. One is the logical level, which is the software level, and another directly at the physical level in terms of the node of the link or the router itself. Thus, we have a network is a collection of interconnected nodes. Usually, we have a graph for that. And I assume that a node is a link. This is a physical node, which is a link such as a router, whose job is to connect. Now, each router or a link node is connected to every other physical node, and a set of another physical node. Now, each link or actual physical line or link always has a certain amount of, apart from its capacity or the speed at which how much information it can travel. Also, it's in a sense the value of strength, how accurately it is able to send information. If that link is weak, it will introduce more number of errors into the transmission. So that means for weaker links, the job of the physical node as such is to increase an amount of redundancy in the data, or to have improved or better error checking and correction methods till such time the link is repaired or replaced. So apart from routing of information and deciding where to send it to, the node's job will also be, this is the physical aspect of it. The study of this is a different thing altogether, but now I'll by and large be focusing more on the logical aspect of it in this video. So I shall briefly try to examine and but in this video I shall both these aspects, but in this video I shall be concentrating largely only on these other aspects of it. the software aspect of it. But now the topic of checksum hashing itself is so vast and so extensive that lifetimes are not enough to come by to explore and to even sketchily and skimmingly cover all areas and all aspects of it. Now, like I stated in an earlier video, checksum hash functions belong to a general family of hash functions called signature hash functions, of which there are two of them. The other one is being cryptographic hash. So the one is a checksum hash and the other is a cryptographic hash. Now I must start off, or I must begin by emphasizing that these two activities are totally distinct and different, and the role of these two categories functions play is also different. Whereas the primary use of a checksum hash is largely for data error detection and correction, and as also its allied use of for lossless data compression. The role played by cryptographic hash function, which means that the objective of checksum hash is to reduce the size of the information without losing any of the value of the information and the correctness of the information, exact value, to simply decrease the size of the information by coding only the relevant and distinctive features or characteristics of that larger piece of information in a very, very compact manner, and this can be done to a very high order, very, very high order. And now that is the purpose of functions such as checksum hash and all of that, which means that if you can code certain features of it which can help you to detect, to correct it, the errors as well, because these two activities, invariably if you try to do one, you will end up doing the other also. But the purpose of a cryptographic hash is something totally different. The purpose of a cryptographic hash is to try to obscure and to make the message itself unintelligible to other people other than to those who are sending and receiving the message, so that other people cannot read that message and interpret it and read it. So the purpose of encryption is basically encryption, and decryption is a totally different activity. And to that end, already prevailing systems like PGP systems would come under the category of what are called true genuine cryptographic hashes. Now the confusion has been introduced and created by and large mainly by the existence of the prevalence at that time, which is understandable, but nevertheless the existence of a function in the very popular system of Unix which is called crypt, which what it does is which it takes your password and makes some sort of a number out of it, and uses every time with the probability of two different passwords mapping to the same number being small or some such thing. Now with the introduction of this, and then now the emergence of something what is called as cryptocurrency or some such thing, this confusion has been blown out of proportion, and these two functions or roles have gotten to be mixed. The purpose of encryption and decryption is not the same as the purpose of the function or the role of error detection and correction and data compression. So now the emergence of things like cryptocurrency have only added to this confusion. These two are two totally distinct roles and functions. That must be first and foremost emphasized. So these two terms have come to be mistaken. So that confusion has to be cleared up in the first place. Now I shall come to direct a few simple checksum ways of error detection and correction which can also aid in the data compression. Now we have a number m again of by bit string of length 2 power L dash to be mapped to a value which is a message or a key or information of length 2 power L dash, which must be mapped to a value v of size less than equal to less than s, which is a bit string of length 2 power L, where L dash is much larger than L. So this is the basic idea. Now what we do is we decompose the extremely large message or information into p equal parts. Simplest case here. You can always do a lot of other things. And we also decompose the corresponding code part S into p equal parts. Thus we have let k equal to kp minus 1 whole power p plus kp minus 2 whole power p minus 1 plus kp minus 3 whole power p minus 2 plus and so on up to plus k1 square plus k naught. Okay, so let this key k or the message part or the information part be split into p parts like so. Now we choose an ideal base B for which P ideal and suitable constants depending on L dash and B will exist namely C naught, C1 and so on up to Cp minus 1 will exist such that the value, the hash value, small message digest, which is basically a compressed value, Cp minus 1 h of Kp minus, Cp minus 1 log of Kp minus 1 to the base b whole power p plus Cp minus 2 log of Kp minus 2 to the base b whole power p minus 1 plus Cp minus 3 log to the base b of Kp minus 3 whole power p minus 2 and so on up to C1 log to the base b K1 the whole square plus C0 log to the base b K0, which is h of k, will always be both order preserving and fairly unique. In other words, we can always find such constants. We can divide it into p's fairly raised. The size of the message digest is equal to. So we can do this. Right? We can multiply by certain constants and raise them to the power of. Now, from the discovery of this method, we can learn that there are hidden subtleties in mathematical operations and highly subtle nuances to the construction and the formation of mathematical expressions. So, we can do this here. So, this is one of the ways of performing checksum hashing. I also look at a couple of other approaches we could possibly adopt. One of which is again, another one is I have an information of length L dash here, which is L dash bits. Okay, suppose we perform all, let us say all 4 selections of these L dash, right? So how do you do that? Let's move from left to right, whatever this so we take one bit here out of this. We start with the left and then move the second one, choose the next one, and for that the next one, and for that the next one, and so on. Then move the first one to this, and then like this. Then move the first one to this, and the second, third one from, and so on like this. We can keep doing that, right? In a certain ordered fashion, right? That means that there's a set of all 4 general R selections of these L dash can always be enumerated in a certain distinct order, right? That means we can always, the elements of that R set can be arranged in a unique canonical order, right? Now, if we make such a selection, each of these R selections, say, or a 4 selection, for each choice of elements, the bits, the value of the bits corresponding to them can be 1, 0, or 1, 0, whatever it is. That means for every selection will actually add up to, will come to only one of these 16 possible values if the choice is 4. In general, if the choices are, the number of possibilities will only come to 2 power r. That means every r selection we make will go to one of the values of 2 power r. What if we make a count, keep a table of size 2 power r, which is the count of the number of such values of each of these? Will that fairly uniquely determine whether what this value of this thing is, serve as a basis for both data compression, and compression will be hard to do. It will certainly serve as compression. As we can see now, So what does that mean? Right? Now, if we take a binary string, there are 2 power L dash possibilities, right? Values there. But only if we are interested in the ones in those, only half of them we need to consider. So, which comes up to 2 power, nearly 2 power L dash minus 1. Let us try and see if whether this idea here is feasible or not. Right? Now the value of r, number of choices I wish to make, can be very small, actually, so that I will let that value be, say, some L dash by C itself. Right? So the number of choices will be L dash C, L dash by C. Right? Now if you take these choices, this is the total sum, right? Now this sum itself has been split into how many parts? 2 power L dash by C parts, right? The number of ways of expressing a number n, number of k partitions of n, we know is nothing but n minus 1 C k minus 1. So if we take this sum and split it into 2 power L dash by C parts, in how many different ways can we do it? And if that value, different ways in which we can split, is greater than the value of 2 power L dash minus 1 itself, greater than or equal to that, it means every possible combination of bits can be fairly uniquely represented as that sum, because we can expect all the possible partitions to emerge from generating such a sum. Right? So we shall see if we, now it is n minus 1 C k minus 1, but I shall try to approximately calculate it here. Now I make another and a fairly reasonable assumption that NCR comes up to a value nearly equal to 2 power r times log n by r bits as a bit representation, comes up to so many bits, is a number which takes up roughly so many bits. Okay? So now in order to verify whether this form of hashing condense that fairly uniquely and yet be fairly small in its this thing, we have to check whether L dash C, L dash by C C 2 power L dash by C greater than or equal to 2 power L dash minus 1. Since no more than half the bits will need to be 1, we can either quote the message itself or its exact opposite complement of it. Okay? So that means 2 power L dash by C log CC 2 power L dash by C must be greater than or equal to 2 power L dash minus 1. 2 power L dash by C log 2 power L dash by 2 power L dash by C greater than or equal to 2 power L dash minus 1. Or 2 power L dash by C L dash C minus 1 by C greater than or equal to 2 power L dash minus 1, or 2 power L dash by C C minus 1 by C times L dash greater than or equal to L dash minus 1. As you can see, this will be very, very large, much more greater than that. So even if we take a simple checksum in that fashion, we will most definitely be able to uniquely get a checksum, which will be very, very small comparatively. Okay, if you take each, there will be 2 power r into L dash power r. L dash power r means r into L bits. Therefore, r into L into 2 power r can be very, very small, such as 5, 6, 7, 8, like that. So at most you will have a table of size 256 or 16 or 256 or 32, like this, into L dash power. If even if L dash is 32-bit number, 32 power 4 will only be 4 words or a 32-bit this thing, like that. 256 message digest of 34-bit will fairly uniquely be able to represent that message, large message itself, and can serve as, using it for error correction will not be easy, but it can nevertheless serve very easily for the purpose of error checking. I shall look finally at another simple method, another idea which can be used for error detection and correction. We know that again, if we have a number here, a binary number, if the weights are same, if the sum of the weights of the lower order bits, and we have the next weight here, if it is just one more than the sum of the weights of all of the preceding bits, or slightly, or more than one, or more than that, the order will always be preserved. But having it more means that gaps will be introduced, which is favorable, which forms the basis for many weight-based coding methods to optimally introduce differences. But what happens here, like we were saying, when we wish to perform error detection and correction, what it means is, like we said, several values of the information, several values of the code must come up to the same value of the information. So here what happens now, if the sum of, so one way to try to introduce redundancy where several values of the larger number always come up to the same smaller number, so the smaller number can possibly act as the information for the large, or like that, so that we can try to do that by obtaining what happens if the sum of the weights, here we have a particular sum, this is and then we have the next weight. What happens if this weight happens to be less than the sum of this? That means it will introduce redundancy. The smaller number can now be coded only as this weight alone, in addition to the many different ways in which it can be coded within this. So what happens is, suppose this is the ith bit and its weight is wi. Okay. For every value which is greater, say value x, which is greater than or equal to wi, if we maintain a table of all possible number of ways in which each of these values can code for each of these values can occur, okay, if we do maintain that table there, so if you take a value x which is greater than or equal to that value wi, then value of x minus wi must be if wi were added to the value of x minus w, number of ways in which x minus wi has been computed, to which if we add 1 to it, because you can add wi to the value of x minus wi to obtain x, so the value of number of ways in which you can obtain x will be x plus the value number of ways of obtaining x minus wi, already existing ways. So simply as some kind of a notation, I will say number of ways of obtaining x is equal to number of ways of obtaining x minus wi plus 1 plus the already existing number of ways of obtaining x, which is already there. So this value, right? Now for all values of x which are less than wi, to those, if we add x plus wi to it, number of ways of obtaining x plus wi must be incremented by 1 for all those values in that table. Now if this size of this code there, so obtained by not exactly adhering to the order in which we assign the weights, and the table is fairly easily storable in memory, then we can know what are all the bit patterns and how many different ways in which we can obtain that particular code with redundancy, and the number of ways of obtaining that redundant information. This is one of the ways, possible ways for small amounts of information where the length is not too large. We can think about trying to define functions which introduce a bit of redundancy in it. So these are three of methods. These three methods are some simple ideas at ways of logically at the software level defining error checking, which is related to compression related coding. The actual physical definition is a slightly different approach to narrative, which I had dealt with in another video. Shall look into that separately.